Imagine holding your phone over a plate as if it were a tiny microscope. But instead of looking for cells, it's reading a meal story. A modern food vision pipeline turns that single instant into a cascade of decisions. Find the food, separate it from background clutter, name what's on the plate, estimate how much there is, and translate that into calories, macros, and likely ingredients. This all happens inside a layered engine that blends computer vision, 3D reasoning, nutrition science, and probability. And while it feels instantaneous, each step is full of challenge and craft. How image recognition estimates nutrition, the tech that turns a photo into calories. At the front is image segmentation, the task of telling the model which pixels belong to rice, which to sauce, and which to the tablecloth. Modern systems use convolutional neural networks, CNNs, and vision transformers to produce pixel-level masks. These masks enable the app to treat each region independently rather than trying to label a whole photo as dinner. With a clean segmentation, the next job is classification. What is that segmented region? Is it grilled salmon, stir-fried tofu, or mashed potato? Classifiers are trained on tens of thousands of annotated food images across cuisines, plating styles, lighting, and garnishes, so they learn visual cues that go beyond simple color or shape. In practice, top K outputs are used. The model will return several likely labels and a confidence score, so the UI can ask you to confirm rather than assert a single answer with false certainty. Portion size estimation is the trickiest technical leap. A picture flattens depth. Two bowls taken from the same angle can contain dramatically different volumes. To recover 3D information, apps use several methods in combination. The simplest is reference objects. A coin, a fork, or a credit card placed on the table gives the algorithm a known scale. More advanced phones use depth sensors, LiDAR or stereo cameras to build a quick depth map. Some apps request multi-view photos, 2 shots from different angles, and reconstruct a rough 3D surface using structure from motion techniques. Where hardware allows, time of flight or dual camera depth data dramatically reduces volume errors. Academic studies consistently show that incorporating depth or multi-view inputs reduces portion error substantially compared to single 2D shots. Even so, volume remains a major source of calorie variance because oil, stickiness, and hidden dressings don't always change the outer shape much but add lots of energy. After segmentation and volume estimation, each food object must be mapped to a nutrient entry. This requires linking the identified item to a food composition database, regional sources like the USDA Food Data Central, or proprietary tables that include restaurant variants and common recipes. That mapping is straightforward for discrete items. Apple equals apple. But mixed dishes require recipe disambiguation. A bowl labeled curry could be one of dozens of variants with widely different oil content and thus very different calories. To handle this, systems use recipe priors, most common ingredient distributions for a dish in a region, context signals, time of day, restaurant menu scraped data, and user history, your prior correction that Mum's curry is high oil. The app may present a weighted estimate and ask the user to pick the most likely recipe, a small interaction that dramatically improves accuracy. Because every step is noisy, the responsible system surfaces uncertainty, confidence bands on calories, top K candidate labels, and suggestions like estimated calories, 420 plus or minus 90. This makes the output useful rather than misleading. In real-world evaluations, top 1 classification accuracy for food image APIs varies widely depending on dataset, cuisine diversity, and photo quality. And top 5 accuracy is typically appreciably better. That's why smart UIs show multiple choices and let users confirm or correct. User corrections feed back into continuous learning loops. Every correction is a labeled example that improves the model for that user, and optionally for the global model if the user opts in. There's an important human factor in this loop. Contextual data improves every step. If the app knows you had sushi for lunch yesterday, and you typically order the same item, the model can use that prior to bias the next prediction. If your calendar shows you're at a hotel buffet, the model expects more variety and different portion priors than at home. When wearables are connected, a spike in steps after dinner can change assumptions about portion relevance for energy balance. These contextual signals convert a one-shot photo into a richer probabilistic judgment. From a technical perspective, many research groups and leading vendors have converged on hybrid systems, deep vision models for segmentation and classification, plus geometric or depth models for portion estimation plus probabilistic recipe matching plus user feedback loops. The hybrid approach outperforms any single technique because it plays to the strengths of each method. It also means that the product experience depends as much on UX design, make corrections cheap and rewarding, training as it does on raw model quality. Despite the progress, it's vital to be honest. Photo-based nutrition assessment is an estimate, not laboratory measurement. Errors cluster around mixed dishes, hidden fats and oils, complex restaurant preparations, and deceptive plating. Studies comparing photo methods to weighed food records show mean errors that can be significant for single meals. But interestingly, when users log consistently over time, biases often average out, so trends, e.g., average daily intake rising or falling, remain informative. That makes image logging especially valuable for behavior change. Lowering friction increases adherence, and consistent logging, even if slightly noisy, correlates strongly with improved diet outcomes. Finally, there's a privacy and ethics layer. Food photos are intimate. They reveal eating habits, cultural practices, and sometimes locations. Good apps offer on-device processing options, explicit opt-in for model training, and clear policies about whether images are stored, shared, or used to improve models. For clinical uses, research studies, dietitian workflows, hybrid pipelines where AI pre-labels and human experts validate are the gold standard because they combine speed with the rigor needed for medical decisions, accuracy issues, ways to improve logs, use cases, top apps, and quick hacks. Photo calorie estimates can vary widely from truth, but their practical value comes from reducing friction and improving adherence. Knowing that, the entire product design pivots from be perfect to be reliably useful. That means adopting measurement practices, UI flows, and hybrid routines that minimize error and maximize behavior change. The two dominant sources of error are ingredient uncertainty and portion uncertainty. Ingredient uncertainty arises when a visible dish contains invisible calories, oil, butter, sugar, refined starch hidden in sauces, or cheese folded into a bake. Portion uncertainty is the classic depth problem. Two bowls look the same from above, but contain different mass. Research shows that adding any of the following reduces these errors substantially. Reference objects, multi-angle photos, occasional weighing, and user-defined recipes. Practical, research-backed hacks you can implement today. Place a reference object, credit card, fork, phone, in every photo. This simple habit gives the model scale and reduces volume error by a measurable margin. Take a second angle, 45 degrees, in addition to the top shot. Two angles enable crude stereo and improve 3D estimation without special hardware. The near future is promising. Advances in edge depth sensing, federated learning, improve models without uploading raw images, and recipe inference, models that predict hidden ingredients from visible cues plus context, will tighten error margins. Mixed reality tools that guide a user to pan left or place a card here, and auto-capture multi-view images will make the process smoother. But for now, the pragmatic rule is use AI to lower friction, but pair it with small human anchors for precision when the stakes are high. AI food scanning turns a cumbersome food diary into a habit you can sustain. And habit beats perfection. With a few easy practices, reference object, multi-view, occasional weighing, your photo logs become reliable trend indicators that support real behavior change. Use them to learn your patterns, not to litigate every calorie. The technology is improving fast, the UX is getting smarter, and the hybrid human plus AI workflows are where the real power lives.